Okay, today we're going to come back to tangent lines and just explore this a little bit more. I know that in past notes we've done this several times, but this is kind of one of the key concepts of calculus, the idea of local linearity and the idea that if you zoom in at any spot on some types of curves, if you zoom in enough, they look like lines. So what we're going to do is just review the process of finding the equation of a tangent line, and the form given here is point slope form. I tend to prefer a different form, which I call Taylor form, and this is the one that we wrote in the past where f of x can be approximated by the tangent line, which is f of c plus f prime of c times x minus c. And I am preferential to this because it really feeds into a couple of key concepts throughout the year and then even into Calculus BC. So while both of these are equations of lines, this is going to be the one I tend to favor 9 times out of 10. Also, this is the form that you're going to see most frequently on calculus multiple choice questions. So we're given the graph of x squared minus x minus 2. This is a parabola, and the end goal is to write the equation of the tangent line and then draw the equation of the tangent line on the graph. So the first thing that we need to do is recognize that in evaluating a function or finding the tangent line, we need to know the value of the function and the value of the derivative, as well as where we're doing the tangent line. And so they're telling us that the tangent line is at x equals 1. So our center point is at 1, so we need to know what is f of 1 and what is f prime of 1. Sorry that these don't happen in order of the way that I do it. Even my cat is upset at that. But let's go about this process of finding f of 1 and f prime of 1, because that's what's going to go in here. F of 1 is 1 squared, subtract 1, subtract 2, which is negative 2. And visually we can see that on the graph. At 1 we are at a height of negative 2. And then f prime of 1, in order to evaluate that expression, we are going to need to find the derivative. And that's what we're doing in part A. If y is x squared minus 2, then y prime, or you could call this dy dx, or if our function was named, we could call it f prime of x. Those are all different names to refer to the derivative. The derivative of x squared is 2x, the derivative of x is 1, and the derivative of a constant is 0. So there's our derivative, 2x minus 1. If we evaluate f prime of 1, that would be plugging 1 into this equation, and we get an answer of 1, which means at this point, if we were to draw a tangent line, the slope of that line would be equal to 1. So now that we know that the slope of the tangent line is equal to 1, we have all of the information we need to fill out the equation here. So that's what we're doing in part C, find the slope of the tangent line. We just did that, f prime of 1 equals 1. Part D, write the equation of the tangent line. So our function can be approximated by the tangent line, which is f of the center plus f prime of the center times x minus the center, and in this case x minus our center would be x minus 1. So there's our tangent line equation. That is the equation of this curve. And if you think about this and what we've learned about transformation form, we have a linear function that is shifted right 1 and down 2 and has a vertical stretch of 1 or no vertical stretch at all. So right 1 and down 2 and has a vertical stretch of 1, meaning the slope is 1 for that identity function. So it matches our understanding of transformations. Okay. And then part E, draw the tangent line of the sketch and label the point of tangency. So we'll call that point of tangency occurs at 1 comma negative 2. I'll write it in there, point of tangency. Okay, that's kind of the meat of what we're doing in these problems. So let's take a look at example 2. All right, in example 2, we are given a function and asked to find the tangent line at -1. So they've identified that the center is at -1, so we need to evaluate f of -1 and f prime of -1. Well, in order to evaluate these, we need to know what the functions are, and we're already given what f of x is. So f of -1 would be 4 times -1 cubed, subtract 5 times -1 plus 3. -4 plus 5 plus 3. -4 plus 8 is 4. And then we need to evaluate f prime of -1. In order to do that, we need to have f prime of x. So I'm going to write down what is the derivative of f. Looking at this, it's just a couple of power rules strung together. So 4x cubed has a derivative of 12x squared, and the derivative of -5x is -5, and the derivative of 3 is the derivative of a constant, which is 0. So now we're going to evaluate the derivative at -1. So 12 times -1 squared subtract 5 is a value of 7. 12 minus 5 is 7. So we can write out our tangent line equation. F of the center plus f prime of the center times x minus the center. X minus -1 becomes x plus 1. Not that they asked us to graph this, but so that you can visually see what this might look like. If you were to grab your calculator or graphing utility and picture this graph on the graphing screen, you would see that it is a cubic polynomial that looks something like this. At a value of -1, we are at a height of 4. So there's our point of tangency, -1 comma 4. And then the tangent line is a very steeply sloped positive line, and that's what we have here. Steep, as in vertical stretch by a factor of 7, left 1, up 4, left 1, up 4. In example 3, we are not given an equation. However, we are given information about the function f and f prime, as well as g and g prime. So writing the tangent line equation should be possible. So just to always keep the general formula on every page that we work on, I'm going to write the general formula from which we'll build our equation. In this case, they're wanting us to do this for the function g, so let's actually call this g. So find the equation of the line tangent to g of x at x equals 6. Fortunately for us, the table is at x equals 6, so g of x can be approximated with g of 6. G of 6 is 7. G prime of 6 would be -4, and then x minus our center of 6. Some people might write this as 7 subtract 4, and that would be fine as well. So L of x is 7 minus 4 times x minus 6. Okay. This is the tangent line that approximates g of x. If we did the same thing for f of x can be approximated by our linearization at 6. So f of 6 is -3 plus f prime of 6. There we go. Okay. In example 4, this one actually requires a little bit of thinking about the process. So go ahead and pause the video and read the question and try to develop a plan of attack in your head. Okay, the thing that sets this problem apart from the others is they actually don't tell you where it's centered, or at least not explicitly. They tell us the value of the function. So when we write out our usual c equals, f of c equals, and f prime of c equals, these are the three things that we need to find to write out our tangent line equation. We know that f prime of c equals 2. And from that, we are going to backwards engineer what is the value of c. And then if we know the value of c, we could evaluate our function there, and then we'd have everything we need to write the tangent line equation. So we have to solve the equation, when does the derivative equal 2? When does the derivative equal 2? So in order to do that, let's find the derivative. 4x cubed plus 4x has to equal 2. Now this equation here is also a little bit challenging. It's a cubic, and typically we're not solving cubic equations except in the more advanced algebra problems. So what I'm going to do is I'm going to turn to my calculator to find the value for which this is true. Now there's more than one way to execute on this problem. I'm going to show you my preferred method, which is doing this graphically. So on the left side of the equation, we have one equation, and that's 4x cubed plus 4x. And on the left-hand side, the right-hand side, we have the value 2. And we're going to look for where these two curves intersect one another, and that will give us the solution to the problem. So when I graph the equation, I should get a horizontal line at 2, and we can see that it does intersect the cubing function somewhere between 0 and 1. So if I want to know the exact value of the intersection, I'm going to do a calculate intersect. So press second trace or second calculate, and we want to find where the intersection is. So that's option number 5. And I'm going to move my cursor pretty close to the intersection, and then if I only have two functions graphed, I just press enter 3 times. My first enter says the blue curve is the right curve, my second enter says the red curve is the right curve, and then the third time I hit enter is the guess. And we find an intersection right there at 0.423. So right away, if I quit to my home screen, if I press X, store as, and I'll do the letter C, now I have this number stored in C. Okay, so this is like saying this happens at X is approximately 0.423, which I'm going to store as the letter C. And this is good notation. It works on the AP test to do it this way. This is our number up here, so 0.423 or 424 if we're doing the rounding. And then I want to evaluate the function at C. So how do I evaluate the function at C? Well, I can do alpha C to the 4th, C to the 4th, plus 2 alpha C squared, plus 2 alpha C squared, and that'll tell me what the function evaluates to, roughly 0.391. So 0.3915. And now we have the 3 pieces that we need to write our tangent line equation. F of x can be approximated by the tangent line, which, since I'm using rounded decimals, I'm going to use approximately equal to, but f of c being 3915 plus f prime of c times x minus c. Okay. So this is our approximate tangent line. I rounded to 4 decimal places. They said to 3. 3 is the more common one for the AP test. So L of x 0.391 or 2 and 0.423 or 4. So, all right. The benefit of this problem is it actually required you to think a little bit about it before you started jumping into it, and it exercised our skill in using the calculator, and that's always a good thing, being able to use that calculator. What's the benefit of having a tool if you don't know how to use it? Okay, finally, example 5. Given f of x equals k minus x squared, find the value where this line is tangent to the graph. And this is actually also another good deep thinking question. First off, we see that from this line, our slope is equal to -6. So we are going to be looking for a derivative whose slope is -6. So f prime of x is equal to -2x. And this is like above, where I'm setting the derivative equal to a specific value. What is the value for which the derivative equals -6? So in this case, this happens at x equals 3. So I now know the center of the tangent line. 3 is the value that sets the derivative equal to my desired slope. So c equals 3, and f of c is equal to, well, in this case, k minus 9. We're going to need to find the value of k. We don't know what it is. K minus 3 squared, k minus 9. If this curve, wherever it is tangent to this line, then both the curve and the line are going to share this coordinate of 3, -17. And where did that -17 come from? Well, if 3 is the x value, and I stick 3 into this tangent line equation, -18 plus 1 is -17. So that is my y value. And that's what we're calculating here. K minus 9 is -17. So k equals, in this case, if we add 9 to both sides, -17 plus 9, -8. So what just happened here? Well, I said if f of x is equal to -8 minus x squared, then this line is tangent at x equals 3. Okay, so there's a lot wrapped into that. Let's actually take a look and see if that's what happens graphically. We're going to graph the function into our y1, and we're going to graph the tangent line into our y2, and the two curves should be tangent at a value of 3, -17. Now it's off my graphing screen, so I'm going to have to adjust my view window. Let's lower our y minimum to at least -17. I'm going to go with -25. So there's -8 minus x squared. There's -6x plus 1. And if we trace to where our x value is 3, we should be hitting the point where those two curves are tangent. And visually here, it looks like that's the case. If I were to zoom in, it should become even more clear to us. So I'm going to zoom in. As you can see, the curve becomes straighter as we zoom closer and closer to that point. So again, if I put my cursor really close to 3, that looks like the tangent line. So that's good enough confirmation for me. We can go to the table also and be like, oh, well, at the value of 3, they both have the same value. So, all right, that's it for the notes on tangent line. Example 4 and 5 are much more of the caliber of thought kind of expected of an AP Calculus student. The earlier problems are going to be more like your quick multiple choice questions or the setup for more advanced problems. But 4 and 5, good thought processes. Thanks for watching. Have a good day.